So now we're going to talk about hidden Markov models. And the key piece before we get started into the machinery of hidden Markov models is to understand what we're doing with them and why we're doing it. So let's not get lost in, make sure we see the forest and not just the trees. And so the idea here is this. The idea is that we have this part of speech tagging task, which you've seen in the earlier videos, where we have a sequence of words and we're trying to figure out what part of speech each word belongs to. And that, in particular on this slide, is this sort of red line of labels, right? So we have a noun, a verb, a determiner, a noun, and finally some punctuation at the end. And so that's what we're going to be talking about, for this whole unit. But in particular here, we're going to use a tool called hidden Markov models. This is by no means the only model one can use for this task. It just happens to be one that works reasonably well. The next unit's videos talk about far more advanced ways of doing a part of speech tagging, so if you're thinking about doing this for a term project, please take a look at those as well. But hidden Markov models work reasonably well, and so we're going to spend some time sort of working through them. This is just to sort of look forward a little bit in the class. In subsequent units, we're going to talk about parsing. And so parsing are these green lines up on top. So they say, the verb is sort of the center of the sentence, and it connects the subject of the sentence to the object, and the object has the determiner attached to it. So this sort of like structure of the sentence, some of you may have had to do this in elementary school. We're going to teach computers how to do this, but as a first building block towards sort of deeper sentence understanding, we're just going to try and figure out the part of speech with this sequence tagging model. And the tool we're going to use, one of many, is a hidden Markov model. All right, so what is a hidden Markov model? A hidden Markov model belongs to a bigger class of models called probabilistic graphical models, which we're not going to get into very much at all beyond today. And what a hidden Markov model does is it models a sequence of states. So imagine a machine that has some internal state to it, and it's sort of, as it's processing whatever it's doing, it's moving from one state to the next state. And it does that with some probability. So it's not deterministic. If it's in state A, it has some chance of switching to state B in the next time step, or in the next step in the sequence. And then at each step, in addition to having some internal state, it also is able to emit something to the outside world. So you can imagine like a little blinky light on the side of this machine that blinks red if it's, depending on what's going inside, or maybe green if something else is going on inside. And this is also stochastic. So, state A doesn't always blink red, state B doesn't always blink green. Sometimes red blinks green, sometimes B blinks red, but you can observe it on the outside. And so the idea is that there are two parts to this model, right? There's the model that you can't see, the hidden state, and hence hidden Markov model, the hidden in the name, that's inside the machine, this invisible state internal to the machine that is sort of grinding along one time step to the next. And then there's the visible part, which is the part that is the blinky light on the outside of the machine. Now, of course, you wonder, how does this have anything to do with figuring out parts of speech on sentences? And the short answer to that is that the part of speech is sort of the hidden piece, right? We can't observe the part of speech, it's not visible on the piece of paper. What is visible, though, are the words, right? And so you can imagine you have this machine that goes from part of speech to part of speech, and each time emitting some word. And what we get to view on the piece of paper is the sequence of words this language machine has emitted out to the outside world that you're observing. And now our goal with the hidden Markov model is to sort of reverse that process and say, here's what the machine emitted. What was the most likely set of states internal to that machine as it was outputting each of these visible artifacts, or what we'll call emissions? All right, so here's a concrete example of this. So imagine James ate the food is the observed sentence. So these are x0, x1, x2, x3. X's are the variable that we'll use for the emissions, or the visible output from the machine. And y0, y1, y2, y3 are the internal state. These are the, what the machine is doing. These are the hidden variables that are not observed and that we're going to try and divine from a model combined with the emissions, right? So we're going to look at these words, these assignments to x0 through x3, and we're going to try and figure out what was the likely sequence y0 to y3 that corresponds to them. All right, and so if we do that correctly, we get noun, verb, determiner, noun, right? So that's the idea. All right, so how do we do this? So our model has the following parameters. So the main two parameters are what are called the state transition probabilities and the emission probabilities. So let's talk about them one at a time. So the transition probabilities tell you if a machine is in one state, let's say state A, what's the probability it's going to transition to state A in the next time step, basically stay there. It will also give you the probability if you're in state A in step 1, what's the probability it's going to go to state B in step 2, right? So what's the chance it's going to change? And of course you have all the other probabilities as well, B to B and then B back to A, right? Assuming you had a state space of two possible states the machine could be in. Now of course, when you're doing part of speech tagging, you have many, many more states. You've got nouns, verbs, determiners, adjectives, and so forth, right? And so this probability matrix turns out to be quite big, right? Given that the previous state was a noun, what might follow it? Well, all sorts of things, right? All with varying probabilities, and we need to model those. So that's the transition matrix. So that's sort of how the machine goes from state to state. What we still need to do is the emission probabilities, and this says, if I'm in the state noun, what's the probability the machine would have output James, right? Or what's the probability it would output door, or fence, or run, right? And you'd imagine the probability of run given noun is quite low relative to the probability of door, right? Because one normally, when one thinks of a noun, one doesn't think of a word like run, right? Now it's not quite as easy as saying that one word is always a noun or one word is always a verb. A good example of this is the old man the boat, right? And so old is usually an adjective, right? But in this case it's not. It's the noun. Who's manning the boat? The old are manning the boat. And man is normally a noun, but in this sentence it's a verb, right? Because what are the old doing? Well, they're manning the boat, right? So the old man the boat. And so you can't just look at each word in isolation and look up in the dictionary what its part of speech usually is and just run with that. You need to look at the context. And this is why the hidden Markov model has these state transition probabilities to try and understand how the sentence shifts over time and how it sort of all ties together rather than looking at bits of it in isolation. There's actually also a third parameter, and this is more of a technical detail than anything really interesting. And it's just the state transition probability looks at the previous state to figure out, what's the probability I transition to the next state. Now, of course, there's a special case here. The first state doesn't have a previous state, and so we just need an extra parameter, which is, sentences usually start with what? So we have a sort of initial state probability distribution. All right, so sort of drawn on a separate slide with some names, you can see here the orange circles are the states, the blue circles are the emissions, and we have these three probabilities with these three names. The transition probabilities from state to state, the emission probabilities from state to emission, and then that initial state probability just for that very first Y0 state. All right, so why is it called the hidden Markov model? So hidden, I think we've understood at this point. We have this row of unobservable variables that we're trying to figure out. These are hidden from us. And then why is it called, and it's a model, so that takes care of the hidden and the model part of the name. But what is this Markov piece? And the key simplification that hidden Markov models give is that they assume conditional independence. So they assume that if you know Y0, you know everything there is to know about the probability distribution of Y1. Y1 depends on nothing except for Y0. Similarly, if you know Y1, that's all you need to know to get the probability distribution for Y2. And there's nothing else anywhere in here. No other variable will help you, right? So that's baked into the model. Now, is that a reasonable model? Well, it's actually kind of silly on the surface of it, right? You might want lots of information to figure out what Y2 is. You may even want to look at the words X0, X1, X2, and maybe even into the future, X3, to figure out what the right assignment for Y2 is. But hidden Markov models say, that's all way too complicated, the math gets too hard, it's too tough to model. We're going to make these simplifying assumptions. We're making this Markov assumption that the current state only depends on the one immediate state prior to it. And further, that the emissions only depend on the current state and on nothing else going on in this graph of variables. And so that's the point that's the reasoning behind the name hidden Markov model.